Hi girls, it's always a bit weird doing lessons this way, but hopefully it will be helpful to you. We're going to have a look at a method today called the Gauss Jordan method of elimination. Now, over the last few lessons we've looked at a method of reducing rows in matrices that was devised by a mathematician called K.F. Gauss, sometimes called Gaussian elimination, but we've been calling it row reduction, which is also a common terminology for it. So remembering that with the row reduction method, our goal was to reduce the matrix, the augmented matrix, into echelon form. So echelon form was where generally you had numbers in the diagonals and above the diagonals and zeros below. A refinement of this method is the Gauss Jordan method, in which we continue to reduce the matrix, so we go a few steps further until only the diagonals remain, although I'll show you later that they don't strictly have to be diagonal. This will allow us to read directly from the matrix to find a solution, rather than having to go back to the equation form and substitute as we did in previous lessons. So we're going to have a look at an example. Here is a system 2x plus 3y plus z equals 10, x minus y plus 2z equals 7, and x plus 2y minus z equals 1. We can write this system in augmented matrix form as you see it there. So using the method that we learned over the last couple of lessons, we would try to reduce this matrix here down to something like this, where we have 0, 0, 0 underneath the diagonal. And in fact we've already done that. I won't go through the steps of that because you know how to do that now. But we've reduced this matrix here down to row reduced echelon form here. And we could stop there by going back to the equations represented by this form of the matrix. So for example, saying 12z equals 36, so therefore z equals 3. Then we look at the second row, 5y minus 3z, which we now know is 3, so minus 9 is equal to minus 4, etc. But the Gauss Jordan method continues the transformation of the matrix. So rather than stopping at this point, the Gauss Jordan method continues until above the diagonal are also zeros. Let's probably the best way to illustrate it is by doing an example. We're going to keep going with this example here and continue transforming it using the Gauss Jordan method. Of course, the methods that we're using are exactly the same. So here's our echelon method, echelon matrix here. We're going to continue transforming it. So the first thing I want to transform is this 3 into a 0. So to do that, I substitute row 1 with negative 3 row 2 plus 5 row 1. I'm not going to go through the arithmetic of it, only because I'm doing this at home on my laptop, and to write numbers with the pointer is really painful. So trust me here, we'll just have a look at one of them. So 3 times 0 is 0, 5 times 2 is 10, so 10 minus 0 is 10. 3 times 5 is 15, plus 5 times 3 is 15, so 15 minus 15 is 0, etc. We continue for the second row now. In the first row we now want to try and get this 14 to a 0. So we have a new strategy, and that is row 1 is going to become negative 7 row 3 plus row 1. So plus 6 row 1, sorry. Have I typed that correctly? Hang on. Yeah, that's right. So we go through that process, and that reduces this 14 down to 0. And then finally we want to reduce this negative 3 here down to 0. And we do that by adding row 3 and 4 times row 2. And we get 0 there. Now you can see that what we have is coefficients in the diagonals. So that's equivalent to saying 60x equals 120, 20y equals 20, and 12z equals 36. So at this point I have a choice. I could go through and do some more transformations of rows by dividing the first row by 60, the second row by 20, and the third row by 12, or we can just read off the solutions looking at that. 60x equals 120, so x equals 2. 20y equals 20, so y equals 1. 12z equals 36, so z equals 3. So it's kind of neat, and to me it makes more sense to continue reducing in this way, because it's the lazy option, I suppose, because then you can just read it off the matrix. Alright, well let's have a look at a few properties of these new Gauss Jordan reduced matrices. So remembering that when we were finding row reduced echelon form matrices, the final reduced matrix had certain properties, and that was that the first non-zero element of any row had to be further to the right than the first non-zero element of the row above. And another property was that all 0 rows were always put last. But for Gauss Jordan reduced matrices, those two properties apply as well. But also, if the first non-zero element in a row is in column number k, then all the other elements in column k are 0. So we'll just go back and have a look at our last one. So the first non-zero element in this row number 2 is the 20 in column 2, and there are all 0 entries in that column other than the 20. So in other words, it has to be only one non-zero per column, and it has to be further to the right than the one above it. Okay, pretty straightforward procedural lesson there. So I want you to have a try now at exercise 8.9, and this is in the handout that we gave up on last time. So it's called the solution of linear systems using matrices, and it's the one that's landscape rather than portrait. I want you to go to exercise 8.9 and just try questions 1 and 2.